Welcome to this video on cooling tower performance modeling and selection. Today we'll apply theoretical methods and work through practical steps engineers use to evaluate and choose a cooling tower. This video begins with the NTU effectiveness analogy, a method borrowed from heat exchangers to help us model tower performance. Then we'll explore how to apply and perform the performance equations and calculate outlet temperatures, effectiveness, and more. By the end of this video, you'll be able to model cooling tower performance using the NTU effectiveness method, a structured tool to estimate heat rejection. You'll also be able to walk through a complete selection procedure, identifying the key steps required to size and configure a tower for a given application. And you'll be able to evaluate trade-offs, understanding how tower type, layout, and approach temperature affect both performance and cost. Before we dive into modeling, here's something to think about. How will your cooling tower selection change if your project was in a hot, humid climate where the wet bulb temperature stays very high? So keep in mind that the outdoor conditions are going to affect the performance of our cooling tower. In this lesson, you will learn how wet bulb temperature affects tower size, performance, and ultimately the entire HVAC design. To estimate how a cooling tower performs, we can use a familiar tool in thermal system analysis, the NTU effectiveness analogy. Just like in heat exchangers, it relates the actual heat transfer to the theoretical maximum. The effectiveness, denoted epsilon, compares the enthalpy gain of the air to the maximum possible gain if it were fully saturated by water's temperature. This tells us how efficiently the tower performs its cooling. We define the maximum heat transfer Qmax as using the mass flow rate of air and the enthalpy difference between saturated and inlet conditions. Then the actual heat rejected is simply epsilon times Qmax. With the actual heat transfer known, we can compute the water's outlet temperature. This is done by applying a basic energy balance across the system, using the enthalpy change of the air. To characterize the balance between air and water flows, we define the mass transfer capacitance ratio M star. It relates the air's heat capacity to that of the water. This factor is key when looking up effectiveness values in NTU charts. Finally, we define NTU itself, which depends on the convective heat transfer coefficient, the area and volume of the field, and the heat capacity flow rate of the air. Together, NTU and M star, and let us use effective NTU method to design and predict tower performance. Cooling tower selection procedure. So we begin by defining the cooling load, desired approach, and flow conditions. To fill volume and approach temperature are crucial because they determine how close we can cool water to the wet bulb limit. Next, we assess tower characteristics like volume, fan type, and inlet-outlet water temperatures. Variable speed fans allow tighter control, especially when paired with higher inlet temperature that improve cooling potential. We then compare different tower models using catalog data, matching capacity, fan power, and expected performance and the various wet bulb conditions. Finally, we weight the trade-offs. Larger towers and higher flow rates improve cooling but require more fan power and piping energy. The most cost-effective design balance performance with energy and capital costs. Finally, some key takeaways from this lesson. The NTU effectiveness method provides a structured approach to understanding tower heat rejection and estimating performance. Cooling tower selection must consider more than thermal load. Layout climate and cost also matter. And every design involved trade-offs. A lower approach may increase efficiency, but at the cost of space, water use, or capital investment. Well, I invite you to continue learning on this fascinating topic of cooling towers. To build your expertise, start comparing real vendor curves to your NTU-based predictions. Practice with simulation tools to see how wet bulb temperature variations affect performance and size. And if you want to push further, you can apply multi-objective optimization to weight tower efficiency, cost, and layout impact. Thanks for watching this video. We hope it gave you a practical framework for modeling and selecting cooling towers in engineering design.